Okay, so last time we were talking about CPU scheduling, you remember? So we said scheduling is the problem of having the kernel decide what process to run next after a context switch. We said there could be various goals a scheduling policy may seek to achieve, and that depends on what matrix you're trying to optimize for your system, whether it's the response time, throughput, reduce waiting time, or some other goal. Okay, the key point, takeaway point there was, although they all sound like good things to shoot for in your system, typically they will conflict with one another when it comes to scheduling. The scheduling tries to make any of those metrics better. It's usually at the expense of some other metric. So you cannot optimize simultaneously all of them. So you really have to decide what is the OS trying to do, what kinds of users is it trying to service, what kind of applications, pick the right scheduling policy for that kernel. Okay, we looked at 3 or 4 different scheduling policies. First come, first serve. Okay, you serve them in the order in which they come in. Preemptive, non-preemptive policy. Okay, round robin is a preemptive policy where you have time slices and you cycle between all of the jobs. We looked at shortest job first and its counterpart SRTF, shortest remaining time first. These policies try to schedule jobs so as to optimize waiting times. Okay, and the last policy which we were talking about towards the very end of the class was MLFQ, multi-level feedback queue. So I'm going to finish that material before switching to today's topic, which is going to be on threads. Okay, so just a quick recap of what MLFQ is. Said it's an approximation for SJF. Okay, we said shortest job first has this disadvantage that it's not feasible or practical because it requires job lengths which we'll never know a priori. Okay? So we would like to approximate it. And we said the good property about SJF is it minimizes wait times, and it does so by favoring short jobs, which are IO bound jobs over CPU bound jobs. That rather than using a job length as a way to implicitly favor IO bound jobs, let's explicitly favor IO bound jobs by observing their behavior at runtime and deciding which jobs get priority. Okay, so the policy uses multiple round robin queues. Within each queue, you do round robin. Okay? The queues have decreasing priority. Okay? The top queue has the highest priority, lowest queue has the least priority. Okay? The time slices also increase as we go down exponentially. And the way the policy works is it always starts from the top and picks the first non-empty queue every time it has to make a scheduling decision. Pick the first non-empty queue and do round robin within that queue. Okay? And whenever you schedule a job, if it does IO before its time slice expires, you bump it up in priority, which means next time it comes to the ready queue, it's going to be one level high if it's not at the top. And if a job actually uses its entire time slice, we label it CPU bound. Okay, and CPU bound jobs we want to favor less than IO bound, so we drop them in priority. So typically CPU bound jobs will sink to the bottom queue, IO bound jobs will rise to the top queue. And because this is a priority scheduler, we are favoring IO bound jobs because we always start with the topmost non-empty queue. So we will favor implicitly IO bound jobs. Yeah, yes, question.
So using entire time slice, you're going down priority, and then if you do a higher job before it comes up, you go up. Is there anything to stay the same after each job?
Okay, so question is there any way to say the same? Typically for the middle queue, there is no way to stay the same because you are either going to drop or rise. The only way you are going to stay the same is if you are in the topmost or the bottommost, because you cannot drop any more or rise any further. Okay? So you will, in the middle queues, you will always decide based on what happened in the time slice whether to bump up the job or drop it. Okay? So, yes, there's a question.
It only gets one time slice before it gets dropped or.
Yes, after every time slice, you adjust the priority of the job. Essentially, by dropping or lowering it, you're adjusting the time slice, right? So you get a time slice, you see what happened in that time slice. Either you will increase the priority or drop the priority. Okay, so you continuously adjust. So if the job behavior changes from IO bound to CPU bound, the algorithm will adjust as well. Okay, so quick exercise, we will not belabor the point here too much. So same 3 jobs, not 3, but I mean different set of 3 jobs, lengths of 30, 20, 10. Okay, no IO. Context switch time is 0, again time slice of 1. So you basically have to emulate on paper what MLFQ is going to do. Okay, so all jobs always by default start in the topmost queue. When you don't know anything about the job, it comes in, you say let's give it the highest priority. Okay, so you start at the top and then you observe. Okay, so what is going to happen? Each job is going to run. Okay, the job with length 30 runs. Okay, they're all CPU bound here. Okay, so it's going to run for 1 second and then it's going to drop. Okay, so it's going to be moved to the next queue. But you always start here, so there are 2 jobs remaining. So run the next job, same thing happens. It uses a time slice, you will drop it. You run the last job here in this queue, okay, and it's going to again use its time slice of 1 second, it's going to drop. So after 3 time slices, here all 3 jobs have moved 1 level down because they're all CPU bound. Okay, so now the scheduler starts, the top queue is empty, so it's going to start with the next top non-empty queue, which is the second queue. Okay, it's going to do round robin here. Okay, so you run the first job. Okay, it's going to use up. Now you give it a time slice of 2. Okay, time slices increase as you go down. So you get a time slice of 2. It uses its time slice, that job drops. Okay, you do this. The second and third job, they will drop as well. Okay, so after 6 time slices, all of those jobs have fallen to the lowest queue. And that's where they stay because they're CPU bound, and here you're going to actually do round robin. Okay, so you're going to cycle between them, give them time slices of 4, okay, until all jobs are finished. Okay, yes, question.
So the priority doesn't go up unless there is I/O?
Yes, the priority never goes up unless you do I/O. If your CPU bound job, your priority keeps decreasing until you fall to the bottom queue. Here you get the longest time slice. You get to run for long periods of time, okay, because you are CPU bound, and that's what you should do for CPU bound. So only way your priority will increase is if you do I/O somewhere in between. Okay, so here is some notation. Okay, so this is you can use whatever notation you want in class exercises, homework, exams, or whatever, so long as you explain what it is. This notation basically, the big numbers are the job IDs 1, 2, and 3. Okay, the subscript is the time that has elapsed in the system. Okay, this is just for you to keep track of what's going on. And the top, the superscript is how much time that job has received. Okay, so 212 says this is job 2. It has received 1 second of computation so far, and the current time in the system after that time slice ends is 2. Okay, so at time 2 seconds, first second this job runs, second that job runs. So at time is 2, it's received 1 second. Okay, and then of course it's going to drop as well, and so on. Okay, so what you see is the jobs are dropped here and then they stay here and they're just, you do round robin until the first job ends, okay, or rather the third job ends. Yeah, time, because it needs 10 seconds of computation, so it ends at this point. And then you only have jobs 1 and 2, you cycle between them until job 2 ends and then job 3. Okay, so I didn't show all of the subsequent rounds, but if you work it out, you will see essentially at job 10 is going to end time t equals 32. That's when it receives its 10 seconds of computation. Okay, job 2 ends at 53, job 3 ends at 32. Okay, completion times are here. Okay, wait time, as I said last time, is always completion time minus execution time, or the job length. Okay, minus arrival time, but here arrival times are 0. Any questions here? Okay, yes, question.
If one of the jobs has I/O in between, when we are counting the time, would it, or the work, would it be bumped up by the I/O and then plus the job work done?
So let's say, so you have to figure out, so you're asking what happens when you do I/O. You have to figure out what instant the I/O happened. Okay? Let's say you are given a 2-second time slice and the I/O happened at the end of the first second. So you are basically have gotten 1 second of computation time. Then you do I/O, so the quantum ends, because when you do I/O, it doesn't matter what time slice you're given, you relinquish the CPU. So you increment the amount of CPU time you have received by 1 second in this case, and then you do I/O, but when you rejoin, you join at that point. Okay, the other thing to keep in mind is how long the I/O takes. The I/O is going to take 10 seconds, then you have to take that out of the ready queue for 10 seconds, have the other jobs compute, and then put it back. That's what would actually happen. So it wouldn't instantaneously appear there just because it did I/O in the top queue. It is going to go to the wait queue and rejoin at a later time. So you need to know when the I/O happened, how long it takes, when it rejoins. All of these details have to be figured out before you can decide. Yes.
When we're doing charts like this and it doesn't specify how long I/O takes, should we just assume that's instantaneous?
Okay. So question is, if it doesn't specify how long I/O takes, should we assume it's instantaneous? First of all, if it doesn't specify that, that is an incomplete specification of what you're supposed to do. Okay. So typically it wouldn't do that. So the next example is actually going to show you what it's doing here. Here one job does I/O and it says that you do 1 second of I/O. So the I/O takes 1 second. So typically all of that should be specified. Otherwise, there's an incomplete specification. And you can of course make some assumptions in that case, but that shouldn't actually have to happen at all. Okay, so all of that, you have to work through it. You need to be told exactly what's happening. Otherwise, you cannot actually figure out when they end, when they join, etc. Okay. Any questions? Okay, so this we'll do this quickly again. Okay, so now just to simplify, there are only 2 queues, not 3. Okay, same 3 jobs. Okay, the first 2 jobs are CPU bound. The second job is doing I/O. Okay, and essentially it says it does 1 second of I/O every other second. What that means is you get 1 second of computation time. Then the next instruction is you do I/O. Okay, then you basically, and then you do I/O for a second. You rejoin the queue. And then once you get another second of CPU time, a time slice, you will do I/O again. Okay, so after every second of computation, you do I/O. That I/O takes 1 second. That's what it says. Okay, so it, in some sense, it's specified what needs to be done. Okay, context switches are ignored here. Okay, so I'm going to just show that solution quickly. So what has happened here is you run 1, 2, and 3 in order. Okay, 1 and 2 are CPU bound, so they are just going to drop. Okay, 3 is an I/O bound job. Okay, so it runs for its 1 second. Okay, and then it goes off and does I/O. Okay, you can assume whether the I/O instruction could be the last instruction of that second, for instance. That's an assumption you may make, or it could have been the first instruction of the next time slot. But here, for simplicity, we'll say it runs for a whole second, and as time slice is about to expire, it goes off and does I/O. Okay, that's an assumption we have made. It's not stated in the problem, but in the solution, that's the assumption that's in there. So it gets its 1 second, time is 3, it goes off, does I/O, so it's going to sit in the wait queue for a second. While it does that, you have to come here and start processing. So this queue is empty, because 1 and 2 have dropped and 3 has gone off to do I/O. So and 1 and 2 are actually in the second queue, so you're going to compute on them. Okay? So you run this job 1, give it a time slice of 2, so it's going to run for 2 seconds. Okay? It's going to use its entire time slice, so it stays there. At the end of its time slice, 3 is back because it only needed 1 second of I/O. Okay? And now 2 more seconds have elapsed, so it's back, it's rejoined the top queue. So since it's a prioritized scheduler, it will run again. Okay? Once it runs again, it runs for a second, does I/O, it goes off to the wait queue. Okay? And then that queue becomes empty. The scheduler comes back here, that's an empty queue. This is the non-empty queue. 1 is already run, so it's at the back of the queue. It's round robin, so you run 2 next. 2 gets 2 seconds. Okay? By the time its time slice finishes, 3 has come back because it needed only 1 second. Okay? So it's going to come back. So what you're going to do is you're going to alternate between 3 whenever it's back and then running a job here. So you're going to cycle between these 2 jobs and 3. Okay, until 3 finishes, it's the shortest job here. So it's going to finish here. Okay, and then you only have 2 and 3 to run. So you just run them in round robin until they're finished. Okay, little more complicated example when you have I/O, because you have to track which jobs are CPU bound, which are I/O bound. When does the I/O happen? So when are these jobs off the ready queue? When do they come back? And when they come back, you schedule them. Okay. Any questions here? Yes, no. Okay, you have to go back and work through this just to get the hang of it. It's fairly straightforward once you understand what's happening. Okay, always, so the MLFQ is fairly mechanical. It's just going to start at the highest queue and pick whatever job is at the head and start scheduling it. That queue is empty, you go to the next queue, pick the job and schedule it. Okay, and at the end of each time slice, you have to ask, is this a CPU bound job? Did it use its time slice, or is it did the job do IO? If it did IO, then you act accordingly. You take that job out, assume it's doing IO, schedule the rest. When it rejoins, you reschedule. Yes, question.
What if you have like 3 queues? Then what happens when you hit IO? Does it go up 1 level or does it go up 2 levels?
Yes. So whenever so question is what happens if there is more than 2 queues, and what happens when you do IO? If you are let's say your CPU bound job somewhere down here, and you do IO. Every time you do IO, you rise 1 level. Okay? So if you are let's say you transition from being CPU bound to becoming IO bound, you'll keep jumping up until you reach the top, and you continue to do IO. And every time you compute, you start dropping. Okay? So you won't directly join the top queue. You're just going to rise 1 level. Okay? So if it's a transient IO and you go back to being CPU bound, you'll drop again. If you're now going to do a lot of IO, you keep rising. Okay? 1 step at a time. Any other questions on this? Okay, so what you should realize is this algorithm is approximating shortest job first by favoring IO bound jobs, and we have not requested the algorithm to know job lengths or anything like this. You are just observing what happened in this time slice and acting accordingly. So it's a nice approximation, fully practical, no need to find out job lengths or anything like that. Adapts to changing behavior. Okay, if the jobs transition from being CPU bound to IO bound and back, the algorithm adapts as well. Okay? As soon as you start doing IO, it will react. Okay, so you don't need to know what's going to happen in the future in terms of being CPU bound or IO bound. You always observe and you decide what to do. Okay? So it's a good approximation. The only issue that we haven't dealt with that was a disadvantage of shortest job first, okay, is starvation. Okay, remember in shortest job first, I said if you always have a short job in the system and there are some long jobs waiting, the short jobs get priority. The long job may never get to run. Okay. Now the same is true here. So we haven't actually dealt with starvation. So if there are CPU bound jobs that have fallen to the bottom queue, and there is, let's say, lots of IO bound jobs, so at the beginning of every time slice, some IO bound job becomes ready to run. So you pick that job, you schedule it, it goes back to doing IO, but before you pick something that was CPU bound, the next IO bound job becomes ready. Okay? So if there is always a short job, you are going to favor. This is a prioritized scheduler. So always going to schedule the highest priority job, which are essentially the jobs that sit in this queue. In our case, they are definitely IO bound. So it is also possible in this scheduling algorithm to have starvation. There are lots of IO bound jobs that continuously become ready to run. The CPU bound jobs are sitting in the bottom queue, lowest priority, and they don't get to run as a result. So that's the only thing that we haven't addressed as far as the limitation of SJF is concerned. All other issues we have dealt with. Okay, we also used round robin for fairness. And so the last question is, how do you deal with this? So we'll have a quick discussion and then we'll move on. Okay, so how you cannot actually have CPU bound jobs really star in the system. Okay, so that's going to cause some problems. Your users of your kernel will be unhappy, saying, I have this job, it's just doing a lot of computation, it doesn't seem to be making any progress. Okay, because you may be doing lots of GUI activities. You sit and keep clicking on your browser as IO. Okay, so your browser is going to get priority and some job running in the background will just sit there and not compute at all. Okay, you don't want bad properties like this. Okay, so what might you do? Yes.
You can make a time slide for QB cell, say you queue run for 10 seconds, then you shift it to the next queue rather than keep it running.
Okay, so we already have preemption here. So if at the end of each time slice, you are going to actually drop the job. So the question is, how do you prevent starvation? Are you saying you shouldn't do priority scheduling? Is that what you said?
You know, let's say that if the job running in the same queue for too long, and you just shift it to run the next queue rather than.
Okay, so suggestion being made is if a job is sitting in a high priority queue for too long, then you just decrease its priority. Okay, just penalize it, saying you seem to be hogging the high priority queue, so you are going to penalize you. Okay, that's what you said. Right? Okay, that's fine. You can do that. Might work.
Like a super time slice where each queue gets around, every queue that's not top one gets around a little chunk of it.
Okay, so you're saying maybe we should think about, if you haven't run, you should try to address that issue somehow by having some sort of time slot. Okay? So both of those ideas are actually along the right direction. So somehow you have to decide if starvation is occurring and address it explicitly. The algorithm by itself is going to start starving jobs if there are these high priority IO bound jobs always ready to run. Okay? So you have to track. One way is you can penalize the high priority job and decrease priority. Okay? The other way is you do the opposite. Okay? So if you say, I'm going to track for every job, what was the last time they ran on the CPU? And after a certain threshold, you say this job hasn't run for 30 seconds. That's half a minute. So it's basically starving. So I'm going to actually take it out of the low priority queue and stick it one level up. Okay? Just to see if it gets a chance to run. Okay? Because you say I'm explicitly tracking whether jobs are starving. And if I see some jobs starving, I'm going to actually start moving them up, okay, as a heuristic. Okay? Which is opposite of saying I penalize high priority job. You say you track starvation and you try to favor the jobs that are starving a little bit. You say, okay, this job is starving, I'm going to give it a higher priority. If it still doesn't run for a while, you keep bumping it up until it eventually reaches the top. Okay? And then it will run, okay? Because it's now a high priority job. And then it will drop again because it's a CPU bound job. Okay? So it's not a good way, but it is a way to ensure that you will not have very bad properties where you can go for an entire hour or something without a job run. Okay, so most kernels that actually implement MLFQ have some sort of dynamic priority where they try to track starvation. They basically have some sort of a timer associated with the job. The job is sitting in the ready queue, hasn't run. You just increase its priority, keep increasing it until it gets to run. Okay? Simple fix, sort of works, okay, but that's all you can do at the moment unless you change the scheduler. Okay? Any questions here? Okay, so last scheduler is called lottery scheduling. Okay? This is the only scheduler we will look at that is actually randomized. All other schedulers were deterministic. If I gave you a few jobs, I told you the job length, I specified the scheduling policy, you can actually write out the order in which those jobs are going to be scheduled and when they finish. Okay, this one is randomized, probabilistic. Okay. So what happens here is every job is given some number of lottery tickets. Okay. The lottery tickets determine how much CPU time you are going to get in the system overall. Okay. So what happens is the way the scheduler runs is every time it needs to make a scheduling decision, it goes to the ready queue, okay, and takes all the jobs and their lottery tickets, you put it in a hat and you run a lottery. Okay, you pick a winning ticket. The job that holds the winning ticket gets to run next. Okay, so every time you have to make a scheduling decision, you run a lottery. You have all the ready jobs, you take all their tickets, okay, and you pick one. You randomly pick one. That's why it's randomized. Because you don't know before you run the lottery which job is going to get. It's probabilistic. Okay, the idea here is by controlling the number of lottery tickets, you can actually get interesting properties on which job gets to run, with what probability, how much CPU time are you going to get on an average, and so on and so forth. Okay, so I'm going to show you an example. And this is best understood by examples. So we'll assume there are two kinds of jobs in the system, short jobs and long jobs. Okay, you can give whatever number of tickets you want to whatever kind of jobs, and we'll see different scenarios and different sort of end result. Okay, so we are going to assume here, okay, for simplicity, that you are going to get 10 tickets. Short jobs get 10 tickets, long job gets 1 ticket. Okay, and here we assume that there's one short job and one long job. Okay, yes, question. How do you determine the kind of a job? That's a good question. So here the number of tickets are explicitly specified by the user. Okay, unlike in the other case where the priority was dynamically determined. Okay, so by default we will say whenever a job starts up, it gets one lottery ticket. Okay, so if the user is not going to tell the OS anything, it's going to give it a default number of tickets, say 1. Okay, so if there are two jobs running and you have 1 ticket each, the probability you win the lottery is 1/2, 50%. Okay, so you have lottery between 2 tickets, you will win with half the times you win, half the times the other job. Okay, so every time you have to schedule, half the time this job runs and the other half. So you basically get 50-50. That's 50% of the CPU time. Okay. Now, if one job was given, just to give you an example without doing that, if one job was given 2 tickets by the user and the other job is still has 1 ticket, that's the default, then that the probability with this job wins is 2/3, and this one is 1/3. Okay, 66%, 33%. Okay, this job is twice as likely to win as this job because it has twice as many tickets. Okay, it's a fair lottery. So the more tickets you have, the more chances you have at winning. Okay, now, if you have 2:1, 2 jobs with tickets, one has twice as many, this is going to get 66% of the CPU time. This is going to get 33%. Okay, because that's going to win the lottery twice as frequently. Okay, so you can control the number of tickets and allocate appropriate amount of CPU time. Now you asked a good question saying, first of all, how do you know whether the job is long or short? Okay? The user has to decide how the user decides is not specified by the policy. You're just assuming that, let's assume you know this job does IO or this job does more computation. You can approximate it by saying that may be long job or short job and vary the number of tickets. By default, the system will give it 1 ticket and treat that job like any other job. But the user has control over how many tickets you get. Okay? Questions here? Okay, so we'll run through this quickly. Okay, 1 short job, 1 long job. Okay, short job gets 10 tickets, long job gets 1 ticket. What's the probability with which short job wins the lottery? That's a 91%, but let's see where you got the 91%. Yes. Okay, so how do you figure out what's the probability with which you win the lottery? Okay, you're going to put all the tickets in a hat, first of all. Okay, how many tickets do you have in the system? Okay, you have 11 tickets. 10 given to the short job, 1 given to the long job. The probability with which you win the lottery is proportional to the number of tickets you have. Okay? So if there are 11 tickets, a short job has 10, so 10 out of 11 times you are going to pick its ticket. Okay? Because assume that each ticket is picked with equal probability. So 10 out of 11 times you are going to win the lottery, and 1 out of 11 times this is short, this is long. Okay? 10 out of 11 is actually 91%. You could have just written 10 or 10 over 11. 1 over 11 is the probability with which the long job runs. Okay? So this job is actually going to be favored a lot more than the other job. If it was indeed IO bound, it won't actually get 91% of the CPU because most of the time it's off doing IO. But if they were 2 CPU bound jobs, okay, and you gave it 10 times as many tickets, you're going to get 10 times as much CPU time, which is approximately right. Okay? So next scenario is no short jobs, only long jobs. 2 long jobs, okay, and the percentage of time each long job gets is what? 50%. Okay. So each of the long job is 1 ticket. Okay, so and there are 2 of them, so each one wins the lottery with probability half. Okay, flip it. 2 short jobs, no long jobs. Probability of the short job winning the lottery. How many tickets do we have? Okay, 2 jobs, each gets 10 tickets. Okay. So what's the probability with which the job is going to win? %, right? So nothing has changed. Just because you gave them more tickets, they still have the equal number of tickets. You give 2 jobs 10 tickets each. You run a lottery over 20 tickets and each has 10, they're still going to win with probability half. Okay, 10 over 20 is still half. Okay, so basically all you have to do is the probability with which a job wins the ticket is the number of tickets you have divided by the number of tickets in the system. Okay, this is 10 over 20. Okay, so even in this case, although you have 10 tickets each, there are two short jobs, they have equal number of tickets, so they get equal CPU time, 50%. Okay, that's 10:1. Okay, long job has 1 ticket, short job has 10 tickets each. There are 10 short jobs, 1 long job. Okay, so that's what's the probability with which a long job is going to win? Okay, 99. But let's do the fraction. How many tickets do we have in the system? Okay, 100 tickets to the short jobs, 1 ticket to the long job. Long job has only 1 ticket. Okay, so that's the probability with which it's going to win. Okay. Short jobs have 10 tickets each. That's the probability with which any short job is going to win the lot. There are 11 jobs in the system. Okay. So this one gets approximately 10% of the CPU time each. That one gets almost less than 1%. Okay. If you flip that around, then you basically have 10 long jobs, each gets 1 ticket each. 1 short job, it has 10 tickets. Okay. So now you have 20 tickets in the system. Okay. So you are going to basically have 10/20 and 1/20. Okay. So that's what's here. Okay. That's how randomized scheduling is going to work. Yes, question.
On that last one, though, each short job doesn't get 50. Oh, wait, yes,
Each short job does get, well, there's only one of them, right? So it's going to, of the total time, right? So these get 50% aggregate, and there are 10 of them, so they split it, so they get 5% each, so that adds up to 50. This one gets the other. Questions here? Okay, so that's lottery scheduling, and we are really done at this point with CPU scheduling. Just quick recap. Okay, so FCFS, simple preemptive, non-preemptive scheduler, round robin, fair, preemptive. Okay, shortest job first, shortest remaining time first. Okay, round robin is also fair. Shortest job first is clearly not fair because it's explicitly favoring short jobs, so that cannot be fair. Okay, but it's optimal for waiting times. Okay, multi-level feedback queues. Okay, it's an approximation of shortest job first. Incidentally, that's the one that many Unix-like kernels actually implement. So that's what you'll see in many kernels. Lottery scheduling is a randomized scheduler. Typically not used by CPU scheduling algorithms, but there are implementations of them out there. Okay, so we run through 5 of these scheduling algorithms. So we are going to, the other assumption we made is context switches don't take any time. Typically context switch overhead is not 0. Okay, it's non-zero but somewhat low. So typically that is going to actually intrude into the amount of CPU time you are actually going to get. And we assume it was 0.
I think I remember you mentioning that Unix-like Unix-like kernels had a time slice of 200 seconds. Is that just the size of the biggest queue? Or?
Okay, so question is, I had mentioned that typically the time slice in Unix, like actually Linux is what I had mentioned, was 200 milliseconds. Is that the time slot of the biggest queue? Right, that's what you're asking. So there are 2 ways to think about it. One is indeed it is the longest time slice you can get. Okay? The other is in that scheduler actually it was not necessarily a full multi-level feedback. It was sort of a round robin with some other type of priorities and things like that. Okay. Typically you don't want anything much bigger than 100 milliseconds because then the time slice gets too large and too coarse-grained. If millisecond to tens or a few hundred milliseconds is as large as you want to make it. Okay, so we will switch gears. Okay, talk a little bit about threads. Okay, so we are done with processes. Okay, we looked at system calls, we looked at context switches, we looked at scheduling. Okay, so we have sort of we talked about the process control block. So we looked at what are the things the OS kernel has to do to manage processes, creating processes, deleting them, allocating resources, tracking them, scheduling them. So all of that we have done. What we are going to do next is ask the same questions from the perspective of threads. Okay, I am assuming that you have all done 230. So you actually have encountered threads. We will recap what are threads, but the real goal here is not to understand how to do threads programming, The real goal is to understand what the kernel needs to do to manage threads, just as we looked at what the kernel does for managing processes. Okay, but to understand that, you need to sort of really understand what threads are and so on. So there will be a quick recap of that. So what are threads is what we are going to start with, and we are going to look at two different ways of implementing threading, okay, in operating systems today. Look at what are called kernel level threads and user level threads. I'm assuming kernel and user level threads are not something you did in 230. Is that a fair assumption? Did you actually look at user kernel level threading packages? No. Okay. So that's basically typically OS level details you don't need to worry about when you're just learning about threads. So we're going to look at that. We'll say a little bit about how to schedule threads, but although not today because we had overflow from last time, that will defer to next time. Okay. So let's start with the definition. Okay. But before I even start with the definition, you have encountered threads. So let me ask you what you understand are threads. Okay. How do you understand threads? What are they? What did they help you do? How do you think of threads? Okay, forget what's on the slide. I mean, I just want you to think of what you did in 230 and explain to me what you thought were threads. What did they do? Guesses, yes.
When a process gets its own copy of variables, threads would still be like access any global variables that would still be accessing.
Okay. Okay, so threads are things that share address spaces. Okay, that's good. What do they do for us? Inherently, yes.
Give us concurrency similar to using fork processes within one process.
So it gives us concurrency. It allows multiple things to execute concurrently. Okay, so threads are something that allow you to share address spaces. They give us concurrency. Anything else? Remember? Okay, so those 2 points are indeed the essence of what are threads. There are a few other details that we will look at. Okay, so this slide is actually going to define threads in a little more sort of formal way. So we'll say process essentially is the address space, which is the memory allocated to it, the text segment, resource segment, and so on, of the thing that's executing. And the thread part of the process essentially defines the execution stream through that address space. Okay? So essentially a thread is a thread of execute, thread of control that runs through an address space. Okay? It's the thing that is actually executing through the thing, address space that you have in memory. Okay? So you will see that there you can actually have one thread bound to a process, many threads bound to a process. All of you know that because of concurrence. Okay? Each process may have multiple threads of control. Okay? The address space is shared across them. Okay? And then you'll see that you don't need to do system calls or message passing for them to communicate with one another. But let's start with a picture. Okay? So whatever we have mentioned is a process, is actually a single threaded process. Okay, to make it more precise, so when we say process, we assume that it has one thread of control, and that's what this process looks like. So this is a traditional process, single threaded. Okay, so it has some region of memory allocated to it. It has code, data, files, segments, and so on. There are registers and stack, and there's one thread of control running through it. That thread of control says what am I executing right now, and you sequentially step through instructions and execute. Okay? So only one entity is actually executing through this address space. That's a traditional process, which is more formally a single-threaded process. Okay, this is a picture of a multi-threaded process. Okay? That same process that I showed here could actually have multiple things executing concurrently through it. Okay? Each is its own thread of control. Each is its own thread, stream of execution. They all share the same address space. They share the same code. Okay, so what happens is all of the code data is shared, but each thread gets its own copy of its registers and its own stack, okay? Own program counters. Okay? And it executes independently of other threads through the same address space, but they all share this address space. Okay, so there's another picture here, which makes it a little more explicit. Okay, so this is your producer-consumer code written as a threaded process, multi-threaded process. So we assume that the producer and consumer are now threads within the same process. Okay, the producer thread is actually executing the producer code within your program. The consumer thread is executing the consumer code. Okay? Same program, two things executing concurrently. One is executing the producer code, that's a thread. The other thing is executing the consumer code, another thread. Okay? They share all of the variables in this program. They share the heap. They share global variables, okay, not local variables. Okay? So each of these threads has its own program counter, okay, which says where is that thread executed. So this thread is going to sit in a loop, so it has its own program counter that basically just cycles through this loop. Okay? So it has its own instruction pointer. Okay? Same for the consumer thread. It's going to loop here. Okay? So it basically has to track what is the next instruction, and so it has its own register. Okay? So that is what is shown here. Okay? This is the layout of this multi-threaded process in memory. Okay? So this is the text segment, that's the source code that is shared by the two threads. Okay? Only one process. Okay? You will see that there are two program counters, one for each thread. The first thread is cycling through this part of the code, the second thread is cycling through that part of the code. Okay? So two program counters. Each of these threads has its own stack as well. The stack has local variables, for instance. Okay? So there are two stack pointers, you will see. Okay, this is the stack for thread 1, that's the stack for thread 2. Okay. The heap is shared as are global variables. Okay, so that's the heap there. So you see only one heap shared by both of them. Okay, and that's essentially global variable. Those are also shared. Okay. You can have as many threads as you want through your program. Okay, so each of them is going to get its own program counter, own stack. They're all going to share the heap. They're all going to share the code segment. And they just execute the same code, but they execute execute them concurrently. Okay, so I'm just recapping what you may have sort of conceptual understood as a thread. Yes, question.
Would threads be the child processes for?
Okay, question is, would threads be the child processes? So the way to think about threads is they are not independent processes, single process. Okay? So just processes have parent-child relationships. Okay? Threads don't have parent-child relationship with other processes. Threads are things that execute within the same process. Okay? So you will not actually, when you create a thread, I wrote something called fork thread there. That's an abstract call. That's not a real function system call or anything like that. So that's just to indicate you're creating a new thread. I may have as well written create thread there, which is more like what actually you use. So when you do that, you're going to create a new thread. This is not the same as creating a new process. Okay? When you really call fork, you take this process and you make an entire copy. Actually copy its memory contents and you have an exact replica. When you say create thread or fork thread, you're not making any copies. The same process, you just allocate another set of registers, a new stack for that process within that address space. That's what actually happens. Okay? So no new process is being created and there's no real child or parent relationship because you're just doing something to that process. You're creating a new stream of execution through that process, which will be represented by your new thread. Okay? So all of those threads actually belong to that same process that you've invoked using fork thread. Any questions here? Okay, we will come to synchronization soon. Okay, not yet. We are ignoring all of that. Yes.
So there's two program counters. That means that there's two CPUs in this example.
Okay. Question is, it says there are two program counters. So does that mean there are two CPUs? Okay. That's not what it actually means. Just as if you have two processes, each have their own program counter, doesn't mean they actually execute in parallel. Okay. So what would happen is you would have either pick this thread for execution and you will load those program counters. This is just a representation. So these will be stored in the PCB. Okay. The process control block will now have a set of registers for each thread. Earlier you had one set of registers for a process. So when the process is scheduled for execution, somehow you have to decide which thread is actually going to execute. You can't execute them all because there's only one CPU. You're still dealing with uniprocessor environment. Okay, so let's say the CPU scheduler, you use MLFQ or whatever, it picked this process. Okay? Something has to decide, whether it's kernel or something else, we'll see in a moment. Something has to decide which of these threads is going to run. Okay, if you say thread 1 runs, then you load its program counter. That's what is going to run. If you say thread 2 runs, you load its program counters. Okay? So you'll have 2 copies, but you won't actually have them executing in time. You'll have to pick one, just as you had different processes and you chose one. Yes.
If each process counter or
Program.
counter, if it has different, if one of the threads is running, if it's not running, and the other one is waiting, what would the process program counter be?
Okay, so you're asking if one process is running but the other one is waiting, what is actually going to be the state of the process, right? We'll come to that in just a moment. That has important implications on how threads are implemented, what the OS is going to do in terms of the process states and so on. Okay, so that's actually the next set of slides. Yes. How do you differentiate between different threads of the program? Okay, the question is, how do you differentiate between threads of a program? You have to have something that is going to implement thread management. Right? And as we will see, not to sort of keep this a mystery, that something is either the kernel is going to explicitly know about threads and manage them, or you have to have a user level library that's part of the process that's going to manage threads for you. Okay, so something has to be aware of these threads, because you can say this process is chosen. Now who decides whether to execute thread 1 or thread 2? You will say either you let the kernel pick which thread of that process to schedule, or the kernel simply picks the process and something else is going to pick the thread to execute. Okay, but there is something has to track all of this. That there are threads, there are n threads active, and each have their own set of registers, and when that thread runs, thread I runs, you have to load its set of registers. They're completely independent from other threads' registers. But if this thread is executing this code, its registers will reflect the local variables, the program counter, independent of what this other thread may be doing here. Okay? So all good points, that's what you want to understand. How do you manage them? How do you schedule them? Okay, who manages them, etc. Okay, so we'll start with kernel level threads, okay, and then we'll look at user level threads. So as far as the OS is concerned, okay, you can say, does the OS actually know and deal with threads or not? Okay? If you say the OS is actually aware of the number of threads in the process and it explicitly manages them, as far as kernel data structures are concerned, as far as scheduling is concerned, you have what are called kernel level threads. Okay? So these are threads for which there is explicit support in the OS kernel. Okay? The kernel explicitly supports multi-threaded processes. I'm going to back up because I skipped the slide here. Okay? So these are the 4 sort of ways you go from single-threaded process to multi-threaded process. Okay? So this is MS-DOS, ancient operating system. It was uni-programming, only supported one process at a time, no concurrency. You can only start one program at a time, and it supported one thread through that process. Okay? So it only supported single-threaded process, did not have support for multi-programming, neither did it have support for multi-threading. Okay? Here's an evolution that basically you had in embedded system. Early versions of Palm pilots and so on. I don't know if anybody even knows what a Palm pilot is. These used to be handheld organizers. Okay, they ran a small operating system. Those were also single process operatings. You could only have one task running, but they supported multi-threading through that process. Okay? So you have only one process that you can run at any time. No concurrency across processes, but you could have multiple threads. These things here represent threads. Okay? The boxes represent processes. The curly things represent threads within those processes. Okay? Here, this is another evolution. You have early versions of Unix that did not implement threading, okay? But they implemented multi-programming. So you could have multiple processes running, but each process by default had only one thread. So in other words, threading was not supported at a process level. Okay? And this is what you have today. You can have multiple processes. Any general purpose operating system allows you to run multiple processes, and you can have one or more threads. If you have one thread, then it's a traditional single-threaded process. Okay? If you have multiple threads, you have multi-thread. So you support them all. Okay? That's the evolution. What we are looking at is this picture. Okay? We already studied how you manage processes. Now we are going to look at how you manage threads within that process. Okay? So kernel level threads basically is where the OS kernel explicitly supports and manages threads. Okay? Now the thing you want to keep in mind is when you have to do a context switch, when the CPU scheduler runs, when you do a context switch, if you have to context switch between threads of the same process, that is much cheaper than context switching between either different processes or threads of different processes. The reason is when you are switching from thread 1 to thread 2 of the same process, okay, across time slices, you don't need to save all the state of the process and reload the state of the new thread, because the threads actually share quite a bit of state. All you are going to do is save the state of the registers for the thread that is being evicted and load the set of new registers for the new thread. Okay? But all memory management information is the same. They have the same address space, so none of the things that have to deal with memory management have to change. Okay? So you'll either need to save or restore this when you're switching between threads within the same process. Okay? When you're switching between processes or threads of different processes, then you have to save it all, just as you did normal context switches. Okay? So the thing to keep in mind is context switching between threads of the same process, much cheaper. Okay? Less bookkeeping to do as far as context switches. Okay? Now, as far as the kernel is concerned, here it is aware of the presence of threads. This is why we call it kernel level threads. So the CPU scheduler is going to pick the thread it wants to run next. Okay? It's not only going to pick a process, it's also going to pick a thread within that process. So in this case, the CPU scheduler will basically say, I want to run this process next and that thread. And that's what is going to execute. So the kernel level scheduler makes all of the decisions for you. It not only picks the thread, a process, but also a thread within that process. Okay, is that clear? What does kernel level threads mean? Okay, so we'll talk about user level threads and I'm going to show you a quick example. So user level threads are exact opposite. Okay? In this case, the kernel does not support threads explicitly, neither is it aware of the presence of threads within a process. Okay? Thread management is done by a library that is linked to that process. Okay? There's a thread management library that is going to decide what to do, how to manage threads, and so on and so forth. Okay? So the OS essentially sees this process as a traditional single-threaded process. Okay? It is going to assume there are no threads within that process. It is simply going to manage it as a single-threaded process, and there is a library that is going to do all of that extra work as far as thread management is concerned. What that extra work entails is whenever you call thread create or thread destroy, that is a library call, not a system call. In kernel level threads, creating a thread is a system call, because the kernel has to be aware of that presence of thread. It has to explicitly manage them. Right? In user level packages, create thread is a library function call. Method call to a library saying create a new thread. So the thread management library will go and allocate some extra memory for that thread and so on. Okay? So that's an important difference. Thread creation switches from being a system call to just being a library call. Okay? The other thing is scheduling is also different, because the CPU scheduler doesn't know of the presence of threads. It's only going to schedule processes. It's going to schedule a process. If that process actually has multiple threads, the library, the thread management library will run its own scheduler. Okay? And it will decide which thread to actually execute. Okay, so scheduling is a two-level decision. The CPU scheduler picks a process to run. The thread scheduler, or rather the library thread scheduler, picks a thread to run. Okay? So what would happen in this, it is going back to this example, the same code was actually running using a user level threads packet. The CPU scheduler will say run this process. Then you will actually execute at this point not a thread, but you will execute the library scheduler, which will say which thread should I pick, and you say I pick this thread, and then it will actually load the registers and whatnot for you. Can run that thread for you. Okay, so two-level decisions. Okay, so everything is done by a threading library. OS doesn't need to support threading at all. Okay. So the advantage of user level threads is you can implement or write multi-threaded programs even on operating systems that may not support threads out of the box. These could be old operating systems that did not have support for threads, could be newer ones for whatever reason threading was not implemented. This doesn't actually prevent you from writing multi-threaded programs. So all you need to do is get a library that somebody else has written. You could write your own. You can simply use threading calls and use that library to manage threads for you. Yes, question.
Are there
Okay, are there traps to differentiate between user level threads and kernel level threads? Typically, what is going to happen is traps are hardware level abstraction. So they are only going to be used for kernel level threads or processes. There is no equivalent thing here. Okay, I'll talk about that in just a moment. There are some things that are easier, but some things that are hard. Okay, user level threads, more flexibility. Okay, you don't like the CPU scheduling policy, you pick a threading library that implements whatever policy you want. So you decide you want to use lottery scheduling to implement or schedule your threads. Okay? But the CPU is doing MLFQ. Okay? So that's okay. You can just write a threading library whose policy is to do lottery scheduling. Okay? So the CPU scheduler is simply going to pick your process, then the thread scheduler runs a lottery and decides what to do. Okay? So you can actually implement your own scheduling policy for the threads you want to run, okay, and not be bound by the CPU's part. In kernel level threads, you're stuck because you're going to have to go with whatever policy is implemented in the kernel. Okay, if you add a threading library, you can just switch libraries, re-implement the scheduler, do whatever you want, and then pick whatever scheduling algorithm. Okay? Alright, so those are advantages. The last advantage, of course, is thread creation, thread deletion, thread context switches are much cheaper in user level threads than they are in kernel level threads. Okay? The reason is in kernel level threads, any thread management call is a system call. It has to go to the OS. That means you have a trap, you jump to the OS runs and does things for you. Here, it's a function call to a library. Okay, there's not even a need to do a context switch. You simply make a function call, the threading library runs, it does whatever you asked it to do. Okay? Function calls, as you may imagine, within a program or a process are much cheaper than system calls to the OS. Order of magnitude cheaper. Okay, so thread management and user level threads lot more efficient. Yeah, because no system calls, only function calls to a threading library. Yeah, those are advantages of user level threads. Now let's talk about disadvantages of user level threads. Anyone have any guesses on what might be limitations? Yes.
If you have more than one CPU, the threads can't run at the same time.
Okay. So if you have more than one CPU, so concurrency, real concurrency, not concurrency on a uniprocessor, but actual parallelism in multi-core systems is a problem. As far as the OS is concerned, if your user level threads, it sees one and only one process. It doesn't know that there are more threads in that process. Okay? Sometimes there may not be, and sometimes if you have actually used a user level threads, there may be. It's transparent to the OS. So the OS can only schedule that process. Okay? And it can only schedule it on one core. If there are 100 threads, that's tough luck for that process because the OS is only going to schedule it once on one core. Okay, there may be lots of other threads that are ready to run. You won't get parallelism. If you have kernel level threads, you can get true parallelism on multi-core system where thread 1 is actually executing on core 1 and thread 2 is actually executing on core 2 in parallel. Okay? So in much of our discussion has been uniprocessor systems. Uniprocessor, this is not an issue because in any case, is only one thing that can run. Okay, so whether there are kernel level threads or user level threads, only one thread can run. But if you had multi-core systems, user level threads are at a significant disadvantage because you will not get true parallelism. Okay? In kernel level threads, you will get true parallelism. You will actually be able to run threads of the same process on multiple cores at the same time. Okay, that's a disadvantage. Any other disadvantages you can think of?
Yeah, blocking I/O call in one thread would block the entire process.
Okay, so that's I/O is the other disadvantage. Okay, because the OS doesn't know of the presence of multiple threads. If any one thread of that process did I/O, okay, the entire process is going to be shifted to the wait queue. There may be 99 other threads that are ready to run. Okay, the OS doesn't know that they even exist. So all it will do is if any process does I/O, the entire process, or any thread does I/O, the entire process block, independent of what other threads are wanting to do. Okay? In kernel level threads, since you know of the presence of these independent threads, if one thread does I/O, only that thread goes to the wait queue. The other threads may still stay in the ready queue and get scheduled. So the process can continue to make progress even if some subset of the threads are doing I/O. but others are ready to run. In user level threads, you cannot do that. Okay? One process, one thread blocks, the entire process blocks, no progress. Okay? So those are indeed two advantages, or rather disadvantages of user level. Because as you will imagine, the disadvantages of user level threads are advantages of kernel level threads and vice versa. Okay? Whatever is cheap here is expensive there, whatever cannot be done here can be done there. Okay? So I'm not going to go and tell you advantages and disadvantages of kernel level threads, because they're simply the ones from user level thread swapped. Okay, question?
I guess this is maybe more specific than necessarily we want to get, but like so with iOS with something like Grand Central Dispatch, would that be kernel level threads or same with Android, like with async
Okay.
tasks and that sort of thing?
So question about iOS and whether it's user level threads and kernel level threads. So there's a good way to find out. I mean, I'm going to just show you. So if you want to ask, is the program actually running user level threads or kernel level threads? All you have to go and do is actually see what the OS sees and tells you what it sees, and you will know. Okay, so here you see that there are all these processes, and the kernel is actually reporting the number of threads for each process. So this should tell you that this kernel, in this case this is OS X, actually supports kernel level thread, because the kernel is actually explicitly telling you how many threads belong to each process. It's saying that the kernel itself has 81 threads and Java has 68 threads for some reason and so on. I mean, Keynote has some 8 threads. So every process is multi-threaded, kernel sees it, kernel can explicitly schedule it. Okay. Now going back to the question that was asked, so in iOS is also multi-threaded at the kernel level. Most modern operating systems actually support kernel level threads. Okay. So you will actually have the CPU scheduler dispatching, in this case there's the Grand Central scheduler actually dispatching threads for you, okay, by explicitly scheduling them. Okay. Right. So now last point here. I did the advantages, we did the disadvantages already. Okay. Last point here is to say that there are actually hybrid approaches between user level threads and kernel level threads. And this is referred to as supporting what are called lightweight processes. Okay. So user level and kernel level threads are actually two ends of a spectrum. Okay. There are sort of intermediate points. So in one case, single process, there may be lots of threads inside it, kernel doesn't know about it. In the other case, as a single process, lots of threads in it, the kernel knows about it. Okay. You can have something in between, and the way you achieve that is there are operating systems like Solaris, and that's now used to be called Sun OS. Okay. So those actually support hybrid schemes, and I'll show you an example also. So what you have in this case is the notion of a lightweight process. A lightweight process is like a process, but it's an explicit schedulable entity within that process. Right? It's the thing. It's the unit of. It's a unit that the CPU scheduler can schedule. In kernel level threads, pure kernel level threads, each thread within the process is mapped to a lightweight process, so that thread can be explicitly scheduled. But that's not the way it has to be. You will see that there are many mappings possible. There's one-to-one mapping, many-to-one. There are more complex mapping. And depending on what you're trying to do in terms of how you want your threads to schedule, you get many flexible ways of getting your thread scheduled. And here are some examples just to show you. Okay. So if there is one schedulable entity in the kernel, and all the threads of a process are mapped onto that schedulable entity, what that means is the kernel is only going to schedule this. Okay? And then something else has to schedule one of them. So they're all mapped onto this one entity. So whenever this runs, one of those things that are mapped onto this thing is going to actually execute. Okay? So this is actually the user level threads paradigm. Okay? There's one thing within the kernel that is getting scheduled. That's the process itself. Okay? And once the process is getting scheduled, one of the user level threads is going to be scheduled. Okay? That's a pure user level threading package. Okay? You have many-to-one mapping between things that are in user space, which are threads, and things that are known to the kernel, which is a lightweight process. Okay. This is a one-to-one mapping, and this is actually what pure kernel level threads do. There's one entity in the kernel for every thread. Okay. Each thread in the process is mapped onto something that the kernel can explicitly schedule. One-to-one mapping. Whenever the CPU scheduler picks this thing for execution, the thread that's mapped onto it will execute. Okay, because there's nothing to pick, there's only one thread. Here, if this thing is scheduled, somebody has to pick between one of those 4 things that are mapped on. That's what the user level package is going to do for you. Okay? In this case, there is no decision once the kernel has chosen. So in this, these are lightweight processes, and the kernel threads are mapped onto those lightweight processes. So those are the 2 ends of the spectrum I mentioned, a many-to-one and a one-to-one mapping. Here are the hybrid schemes. Okay? Here's a complicated hybrid scheme which says here are user level thread. Each thread at the process level is mapped onto multiple things at the kernel level. Okay? So whenever this entity, this lightweight process is actually scheduled, okay, you can pick any of those. When that one is chosen, you can also pick any of those. Okay? So if you have money course, you can pick this thing, and then in this case you need to do 2-level scheduling. Because the kernel is only going to pick lightweight processes for execution, and then there's a user level scheduler that's going to pick which of the ones that are mapped onto that entity will be scheduled. Okay, so you will pick one of those 4, and you pick this, the same here and same here. Okay. This is actually one process. Okay. Here's another process where you picked one thread and directly mapped it onto a kernel level thread and said, whenever this entity is chosen, run that thread. But there are other threads within that process that are actually sharing a smaller number of lightweight processes. Okay. You will only do things like this, explicit control of how threads at a user level get mapped onto what is visible to the kernel level, when you want to carefully control how threads are scheduled, how they share kernel resources, etc. Okay. You can actually get control over what the kernel sees and does. Okay, so when you create a thread in your process, okay, there are calls that says allocate a new schedulable entity for this process. In that case, you will get basically something in the kernel and that thread gets mapped. Or you can say share something that already exists. You can do this as well. So the programmer can control, okay, when your lightweight process support, how you want threads within your process to be visible and scheduled at the kernel. You have a question in the back.
What's the benefit of combining the 2? Since you already have to use the kernel threads, isn't the benefit of
So if you, let's say, the question is what's the benefit of doing this? So let's say you are kernel level thread. By default, you will be in this mode. Whenever you fork a new thread, there will be something in the kernel that is going to be allocated, and that thread will be mapped onto. So there are 4 threads. There will be 4 kernel level threads. Okay. Suppose you don't want to give that process that much CPU time for any reason. Let's say, okay, you want that to share all those threads to share the kernel level resource. You can say, I'm going to fork threads, but don't allocate additional entities in the kernel. Okay. So you can emulate this model using kernel level threads by saying, every time I say create thread, just map it onto whatever lightweight process already exists for this process. So you can emulate this and have them all be mapped here. Okay. So what this will mean is, although there are 4 threads, you will basically only get scheduled whenever this entity gets scheduled. Here, this process is going to get 4 times as much CPU time if they are all CPU bound, because they are basically each independent schedulable entity. If all of those threads are in the ready queue and you are doing round robin, you will schedule this. So the same process is getting 4 time slices in succession, let's say. Okay. Here you will not have that. You will basically run this lightweight process and then perhaps a lightweight process belonging to another process. So you're actually switching between processes. So you can control the amount of CPU time you get, how they get scheduled. So it's more sophisticated, typically not done by programmers unless you want to get some special properties. Okay. But the threading library for your kernel level threads and lightweight process support will actually allow you to do all of this. Okay. So we have a couple minutes left. We are going to just talk quickly about threading library. So most of you probably have done some Java threads implementation. Okay. That's basically how threads are implemented in Java. Okay. There are different threading not libraries, but different threading interfaces. The 2 or 3 that are very common are pthreads or POSIX threads. Okay. That's the threading package you use if you want to write code in C or C++. The Java threads, that's the interface you use to write threading code in Java. And there is Win32 threads, which is the threading interface for Windows. Now, one thing I'll mention is all of these are APIs that you use to write your code and write multi-threaded code. By default, none of these interfaces, although the interfaces have been standardized, none of them specify whether they should be implemented as kernel level or user level threads. Okay? So you can get JVMs that are actually managing threads at user level. You can also get JVMs that are managing threads at kernel level. Okay? I just showed you a Java process on that activity monitor where the number of threads within that Java process was visible to the kernel. Okay, that's a JVM implementation where the JVM itself is using kernel level threads that are explicitly supported by the kernel. Okay. You have JVMs where the JVM implementation itself has its own inbuilt user level threads library. Okay. In that case, the kernel will not be aware of the presence of threads within that Java process. You will use the same code. Okay, your Java code will not change. Okay, how you create threads, how you do synchronization will not change. How the threading interface has been implemented is changing underneath. Okay? Same is true of P threads, which are essentially POSIX threads. Okay, this is the default threading package in most Unix-like operating system. P threads don't specify whether to use kernel or user level threads. Okay? It's the same. As far as the interface is concerned, you got P threads libraries that are using user level. You got P threads libraries that use kernel level. That's left to whatever platform, OS platform, and whatever library has the library designer chose to use to implement threads. Okay? So what you need to distinguish between our interfaces, which are Java threads, POSIX threads, Win32 threads. They are simply APIs you use to create threads and manage threads in your program. And the implementation. The interface and the implementation may be different. Same interface, you may have different implementation. Some use user level, some use kernel. The choice may also be dictated on what platform you are running. Right? If you have like very ancient platforms that did not have kernel level threads, the only way to execute multi-threaded program is to use a user level package. You can use POSIX threads on ancient operating systems. You can still run POSIX multi-threaded code. The OS is not going to help. The thread library has to do all of the work. Okay? So distinguish between the interface and the implementation. Implementation is where you have to figure out, am I going to use kernel support if it exists? Should I use user level support? If there's no support at OS, you have to only use user level support. And the interface, which is just a JVM that supports Java threads or POSIX threads and so on. Okay? Now, in most cases, the default on modern operating systems is kernel level threads because the OS designer is actually supporting thread. They've chosen to actually support it. So by default, you go with it. That's not the only way. Okay. So that's basically all we have. There's a JVM I talked about. Here are some snippets that you can look at. I'm not going to talk about it. I just tell you how to create threads in different languages. Okay. So there's P thread create, there's create thread and new thread. They're all equivalent in different APIs. Okay. So stop here for today and continue the discussion next time.